Okay, so we've got a question here. It's a very common exam question. We've got carbon monoxide and hydrogen reacting to form methanol. And you've got to have the equation, okay? And we've got to find out the value of Kc from this information they give us here. Well, they tell us that to start off with, you get 0.24 moles of carbon monoxide, and you get 0.38 moles of hydrogen. And they're sealed together and allowed to reach equilibrium. And at equilibrium, the amount of carbon monoxide has gone down to 0.15. Okay, so how would we do this? Well, what I recommend you do, and most people will do it the same way, is I would write down start moles here. And what have we got? Well, we've got 0.24 moles of carbon monoxide and 0.38 moles of hydrogen, and there are no moles of methanol to start off with. Then I do another little column here. Some people leave another row. Look, I'm going to put them down moles used up. Moles used. And then the final column here, we're going to have moles at equilibrium. Okay, so we have got, let's see what we've got. They tell us at moles at equilibrium, look, we've got 0.17 moles of the carbon monoxide remaining. So that means how much of the carbon monoxide we used up? Well, it's 0.24 minus 0.17, which is 0.07. Yeah, okay, so we've used up 0.7 moles of carbon monoxide. Every time we use up 1 mole of carbon monoxide, we use 2 of hydrogen. So how much hydrogen have we used up? We've used up 2 times 0.07, that's 0.14. So we can work out how much hydrogen are we going to have left over. So it's 0.38 minus 0.14, which is 0.24 moles. Finally, we need to just think about the methanol. Moles used up, so that's not applicable, as they haven't used any of it up. There wasn't any to start off with. But how do we know how much we've got at equilibrium? Well, every time we use up 1 mole of carbon monoxide, we make 1 mole of methanol. And how much carbon monoxide do we use up? 0.07. So we must have here 0.07 moles of methanol. We've now got our expression, and this is where we have to be a little bit careful, because we know that Kc is equal to, it's going to be methanol, concentration of methanol, over the concentration of carbon monoxide, over the concentration of H2 squared. Now, it's not the number of moles that goes into this equation, it is concentrations. How do we work out concentration from moles? Well, concentration divided by the volume, and they do give us the volume here. Look, they give us the volume of the container. So what we're going to do is we're going to do concentration at equilibrium. So that's moles over volume. And I'm just going to call the volume V here rather than actually work it out. And we'll see why in a minute. Okay, so I'm going to put 0.17 over V, 0.24 over V, and 0.07 over V. Now you could divide that by 1.5 and then you'd end up with like all these fractions, okay? But what we're going to do is put these values, these yellow values, into the equation here. And so we'll see we can do a bit of cancelling out and make the calculation a little bit quicker. So the concentration of that is, that's going to be 0.07 over V divided by the concentration of carbon, so that's 0.17 over V. And then we've got to remember to square this whole thing. We'll square the whole thing. So that's going to be 0.24 over V squared. So if you remember, that's going to be equal to 0.24 squared over V squared. I'm going to put that into the equation. So 0.24 squared over V squared. Now we can cancel some of those V's out. I'm going to get rid of, so that V there, that one, and that one can go, can't they? So let's rub them out. Okay, so that makes life a bit easier. And what can we do with these? Well, if you're dividing by v squared at the bottom there, that's like having a v squared at the top. So I'm going to bring them up onto the top line, v squared. Then all you've got to do, we know what v is. V is equal to, it gives us a value of v is 1.5. Put all your numbers in and you get kc is equal to, if you work it out, is, you can do it yourself, but I think it's 16.08. Now, all of my data is only given to two significant figures, so I'm going to just call that kc is equal to 16. And the units, well, we've worked out the units for this in the previous video, so it's going to be mole to the -2 dm to the 6. Okay, so that's what we're going to do for that one. Right, let's do another one. One example, that's how you do it. So this is, as I say, this is a very, very common exam question. Actually, what they often ask you to do is they ask you to, they'll give you all this information and they'll stop you at this green line here when you've worked out the moles of equilibrium. And they'll say, in case you get that bit wrong, because then you get Kc wrong as well, wouldn't you? So they say, they have a second part of the question which says, in a different equilibrium mixture, the amounts of moles of the following was this, 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 and then you put them in and put the values they give you into to work out a Kc there. So they just split it into two halves that makes errors carried forward, marking for them a bit easier. But that's the basic question. Right, we've got one more example of this. Okay, so a bit of a more difficult ratio. We've got 3s and 2s here with this one here. Okay, so what do we write down? We write down. I'll try and keep the color scheme the same. So what did I have? I had red, blue, green. Okay, so right, let's write. So we had start moles in this line. The next line is going to be moles used up. And the final line is moles at equilibrium. So let's look at the info they've given us here. How many moles of nitrogen do we start off with? It's 1.4. And hydrogen, 5.5. And we had 0 ammonia. Now, at equilibrium, they tell us you've got 0.7 of ammonia. That's all they tell us. So at equilibrium, we've got 0.7 moles of ammonia. All right, so that's stupid highlighter size doing there. I don't know why that's there. It won't go away. So anyway, where was I? Yeah. So we formed 0.07 moles of that. So that means for every 2 moles of ammonia, we're only using up 1 mole of nitrogen. So we must have used up 0.35 moles of nitrogen. So that is here's 0.35. I think this is the easiest way to do it. And then I think, right, for every 1 mole of nitrogen used up, we use 3 moles of hydrogen. So that means we must have used 3 times 0.35, which is 1.05 moles of hydrogen. So that's how much hydrogen we used up. So at equilibrium then, how much of these things we got left? So, well, we've got 1.4 minus 0.35. So that's going to be 1.05. And hydrogen is going to be 5.5 minus 1.05, which is 4.45. But that's not where it ends, is it? Because we've got our equation. and it's the concentrations goes into the equation. So we've got the equation down is going to be NH3 squared, concentration of over N2 to the power of 1, H2 to the power of 3. Okay, so Kc is going to be equal to Kc is equal to, right, now let's call the volume, they tell us the volume is 3 decimeters cubed, but let's call the volume V. So it's going to be, so concentration at equilibrium is going to be 1.05 over V, 4.45 over V, 0.70 over V. Right, NH3 squared, well, that's going to be, that's that, so that's going to be 0.7 squared, over V squared on the top. And on the bottom line, we're going to have, well, N2, well, N2 is just 1.05 over V multiplied by the concentration of H2. So that's 4.45. Right, that's down here. We've got to cube the whole thing. So 4.45 over V all cubed. Well, get rid of this here, and you've got to cube the top and the bottom of the fraction, haven't you? So that's cubed, and the V is cubed as well. So 4.45 over V cubed. Now we can cancel out some of our V's. So we have got over V squared on the top here. Right, so that means we can get rid of that V cubed and turn it into just a V, and that will work. Okay, that's way that V is going to go. Okay, so simplifying everything, we have got 0.7 squared over all of this bit here. What can we do to those two V's? Well, I'll bring them up to the top line instead. And we're going to have a V squared up there. And we can get rid of the V's on the bottom line. Then all you've got to do is put your numbers in. And you know what V is equal to 3 decimeters cubed. Yeah, 3.0 decimeter cubed, and you will get your answer there. Okay, now you can find lots of examples of these in past papers and so on, but I just want to give you one bit of a strange example. Is when you've got the same number of moles on both sides of the equation. So let's have a look at this. H2 and I2 goes to H2HI. Let's say that they tell us that you start with 5 moles H2 and you start, let's say, 6 moles of I2, and at equilibrium we have formed 1.5 moles of HI. And I'm quite I'm going to be quite obvious here, and I'm going to say they don't tell us the volume of the container. Now, in the previous 2 examples, you needed to know the value of V, the volume of the container, didn't you? We needed to know that. We didn't have it because it ends up here in the final expression. You see, with this one, it won't end up in it. We'll see why. So, H2, yeah, let's start. What was it? Yeah. Used and equilibrium. So start moles of hydrogen 5 and 6. We've got no HI. At equilibrium, we've got 1.5 of HI. I need to balance my equation there, sorry. So if you formed 2 moles of HI, you must have used up 1 mole of iodine. So that's going to be 0.75 of a mole of that. And to form 2 moles of H, I've used 1 hydrogen as well. So that's 0.75 of a mole of that. So the equilibrium, what's going to be left over is 4.25, 5.25. Okay, so let's put down the concentrations at equilibrium. So that's 4.25 over V, 5.25 over V, and 1.5 over V. Right, I'm going to put this equation in here because I think I've got a bit of space here at the bottom. So what's Kc equal to? Kc is equal to Hi squared over H2 times I2. Right, put the numbers in. We're going to get this squared, aren't we? The whole thing squared, which we've said before, is going to be 1.5 squared over V squared divided by, well, H2 is 4.25 over V multiplied by 5.25 over V. Now, we've got 2 V's on the bottom, 2 V's on the top, so they're all going to cancel out, so we don't need to know the value of V. So that's why we don't need to know it. Now, the volumes only cancel out in special cases when you have the same number of moles on both sides of the equation. And it follows on from that, whenever you do have the same number of moles on both sides of the equation, Kc will have no units. So these exceptions really makes it a bit easier to do when you've got the same number of moles on both sides of the equation. Then you don't need to know the volume. And the other famous example that you use all the time for this is, I remember I said in the previous video, is when you form an ester from a carboxylic acid and an alcohol. Carboxylic acid and an alcohol, arrow, ester plus water. You've got 2 moles on both sides of the equation. You don't need to know the volume for those sort of ones either. Okay, leave it there.